Hello students, today we are going to study cyclotron, the particle accelerator. For this topic, you might have studied this topic in your 12th class, obviously, and just we will go thoroughly through this topic, and this is quite important for your examination point of view as well. So, what is a particle accelerator? When you target the particle beam on a particular when you bombard the particle beam on a particular target, you need to acquire some the beam need to acquire some energy, and to target that beam, actually you need some kind of arrangement, and that arrangement always consists of electric field and magnetic field, because to accelerate the charged particle you require some kind of force, and when charged particles happens to be in an electric field and magnetic field, it experiences a force and it's a start to accelerate. Okay, so similarly, in every kind of arrangement you of the particle accelerator, you will always need some kind you will always need electric field and magnetic field. So here in cyclotron there is a combination of both the field. Now how do you comply this composition? So we need to first discuss the construction of the cyclotron. Now it consists essentially of two flat semicircular hollow metal boxes D1 and D2, and here you may be saying this that there are two D1 and D2 are the two hollow metal boxes, and these are also called Ds, and you are applying magnetic field perpendicular to Ds, means in such arrangement that here are the your north pole and south pole, in such arrangement that there is a magnetic field in this hollow disk. Okay, then you are applying a high frequency alternating potential as well on these Ds, and alternating potential means the electric field is continuously varying in a particular D. Okay, so here is your source. In there is a particular space, very small space in between these D's. This is the small space, and here you need in this arrangement, this is your small space, and you need to put your source on this small space between these D's, the empty space between these D's, and there is no we can say that there is no field between this space, and this is for field free region. This is a field free region. Okay, so how does this work? You know the principle of action, where there are two kind of forces, because there are two kind of field, and charge in electric field will experience a particular force, electric force, and charge in magnetic field. Now this particle initially was at rest at this source is emitting the particle, and initially it was at rest. Now when this charge start to accelerate, when this charge leave the ion source with a particular initial velocity v naught, when this your material or we can say any radioactive material, when this charge leaves this ion source, then it has some velocity v naught, we can say, the which is, and when it enters into the magnetic field region, when it enters into the magnetic field region, it follows a particular trajectory, and that is a circular trajectory, because of this force F is equal to K of V naught into B cross. Okay, so because of this force, this particle will follow a circular trajectory, and we know that under the action of this field, the path of the particle is bent into a circle of radius r naught given by this relation. So there will be automatically arrangement of centripetal force equal to this magnetic force, and that's why the particle following this circular trajectory will have a particular radius, and r naught will be equal to, we can cancel out v to v, no, v, and you will get that r naught is equal to m v naught k v. Now when this particle is about to leave this field, the magnetic field is about to leave from here. When this particle starts from here, it follows a circular trajectory, and when it is about to leave from this region, now we need to apply the magnetic field in with such a altercation that whenever particle leaves a particular d, the electric field changes in such a way that it start to accelerate the particle. It accelerates the particle, it kicks out the particle from this d, and the this electric field in this t changes because of this alternating electric field setup. So when this electric field changes with a certain frequency, then when this particle is about to leave the d, it gets a kick and is accelerated into the other d, where now if it gets a kick, if it is accelerated, then the velocity will be something different, and r is directly proportional to v. That implies it has a higher velocity now. So it moves in a semicircular path of comparatively larger radius to emerge again into the gap between the days. Okay. Now the frequency of the revolution of the particle in the circular orbit is given by this. So frequency, we know the relation. Frequency is v upon 2 pi r 1 upon t is equal to, now we put the value of this r into this relation, you will get that frequency is actually independent of velocity of the particle. Okay, and we need to apply this arrangement. Let's discuss this important fact that if the frequency of revolution is independent of the speed of the ion and the radius of path in the d, so if the electric field reverses regularly at a frequency equal to this frequency, so we will apply the frequency of the electric field setup equal to this frequency. That's why the particle always gets accelerated again and again. Okay, and because this frequency is independent of velocity and radius, so this frequency is a constant thing, and every time whenever particle is about to leave the d, it will get accelerated. Okay, so this is also known as the resonance equation for a fixed frequency cyclotron. So this is your cyclotron, and when you need to target the particle, you can have a particular arrangement. You can use a particular target anywhere here, and when this just about to leave, or here, and this is about to leave from here, then you can target the particle on this. Okay, so what will be the energy of this particle? The kinetic energy of the particle can be non-relativistically is equal to this half mv square. Therefore the maximum kinetic energy of the particle when they leaves the cyclotron is, we can put the value of v into this. So this is the value of v. When for the maximum velocity, you need to put the maximum radius as well. Okay, so the velocity kinetic energy comes out to be q square b square upon 2m into rm square, where rm is the maximum radius of the circular orbit. Okay, thus the maximum energy that can be imparted to the particle is directly proportional to the square of the radius of the d's. Okay, so velocity, now putting this value as, so the kinetic energy comes out to be something like this. This is the relation of kinetic energy, and in terms of equivalent voltage, we can have this kinetic energy equal to this potential energy setup. So Wm is equal to Qv. That implies the potential needed to apply it is equal to this much. Okay, so this is your cyclotron topic, and this is too much important for your examination point of view to try to understand this, and this is very simple because you have already studied this into your 12th course. Thanks.